Our planet has a history. It's a history written in stone, ice, and the very DNA of life itself. This history is marked by periods of incredible flourishing and brutal extinctions. These extinction events, where vast numbers of species vanish, are not random. They seem to follow a pattern, a cycle of destruction repeating roughly every 26 million years. This pattern raises a profound question. What could cause such periodic devastation on a global scale? Scientists, captivated by this cosmic mystery, began searching for answers beyond our world. The idea of extraterrestrial causes for these events arose, capturing the imagination. Two theories gained traction: Nemesis and Planet X. Both propose the existence of celestial objects lurking in the distant reaches of our solar system, their gravitational pull influencing a deadly cosmic dance. The search for an explanation for these cyclical extinctions is a testament to the power of scientific inquiry. It's a journey that has taken us deep into the past, analyzing geological records and fossil evidence. It has also propelled us to look outward, searching the cosmos for answers hidden among the stars. The quest to understand these events isn't just about unraveling the mysteries of the past. It's about understanding the forces that have shaped life on Earth and the potential threats that may lurk in the vastness of space. The Nemesis hypothesis emerged from a captivating idea. What if our sun has a hidden companion star? This hypothetical star, dubbed Nemesis, was proposed to be a red dwarf or brown dwarf, much smaller and dimmer than our sun. It was thought to reside far beyond the orbits of even the most distant known planets, lurking in the icy depths of the outer solar system. According to the theory, Nemesis wouldn't be content with simply existing in the darkness. Every 26 million years, it would complete one orbit around the sun. This orbit, however, wouldn't be a simple ellipse. Instead, it would be highly elongated, taking Nemesis through the Oort cloud, a vast and distant shell of icy bodies that surrounds our solar system. As Nemesis journeyed through this cloud, its gravity would wreak havoc. It would disrupt the orbits of these icy bodies, sending some hurtling towards the inner solar system. These icy interlopers, now on a collision course with Earth, would become the harbingers of destruction, bringing about mass extinctions. The Nemesis hypothesis, with its elegant explanation for the periodicity of mass extinctions, captivated the scientific community. It was a chilling reminder that even in the vastness of space, we are not immune to the gravitational influence of unseen celestial objects. While the Nemesis hypothesis proposed a dim companion star, the Planet X theory focused on the possibility of a massive, undiscovered planet lurking in the outer reaches of our solar system. This hypothetical planet, much larger than Earth, was thought to orbit the Sun beyond Pluto, in the cold and dark depths of the Kuiper Belt. The theory suggested that Planet X's gravity, though weaker than a star's, could still be strong enough to disrupt the orbits of comets in the Kuiper Belt. As Planet X moved through its orbit, it would create gravitational ripples, nudging comets out of their stable paths and sending them on erratic trajectories through the solar system. These wayward comets, influenced by the unseen hand of Planet X, would become potential threats to Earth. Some might be drawn inward, their paths intersecting with our own, leading to devastating impacts. These impacts, depending on the size and velocity of the comet, could trigger widespread devastation and mass extinctions. The Planet X theory, like the Nemesis hypothesis, offered a plausible explanation for the cyclical nature of mass extinctions. It highlighted the profound influence that even unseen celestial objects can have on the delicate balance of our solar system. Comets, often described as dirty snowballs, are icy remnants from the early solar system. These cosmic wanderers, composed of rock, dust, and frozen gases, hold the potential for both creation and destruction. While they may have delivered water and organic molecules to Earth, seeding life in its early stages, they can also bring about catastrophic devastation. The impact of a large comet, even a relatively small one by cosmic standards, can release an unimaginable amount of energy. The kinetic energy of the impact is transformed into heat and shock waves, instantly vaporizing the comet and a significant portion of the Earth's surface at the impact site. This initial blast is just the beginning of the devastation. The impact throws millions of tons of debris into the atmosphere, blotting out the sun and plunging the planet into darkness. This impact winter can last for years, disrupting plant life and collapsing food chains. Furthermore, the impact can trigger massive earthquakes, volcanic eruptions, and tsunamis, adding to the global chaos. The long-term effects of an impact can be equally devastating. The massive release of greenhouse gases from vaporized rock can trigger rapid climate change, altering the planet's delicate balance for centuries to come. To test the Nemesis and Planet X hypotheses, scientists embarked on a quest for evidence. They turned to the Earth itself, searching for telltale signs of past cometary impacts. These signs, like cosmic fingerprints, would provide clues about the frequency and magnitude of these events. One key piece of evidence came in the form of Iridium, a rare element on Earth but abundant in asteroids and comets. Scientists discovered a thin layer of iridium in rock layers around the world dating back 66 million years to the time of the dinosaur extinction. This global iridium layer suggested a massive impact event, lending credence to the idea that an extraterrestrial object was responsible for the dinosaur's demise. Another clue came from shocked quartz, a type of quartz created under immense pressure, such as that generated by an impact. The discovery of shocked quartz in layers coinciding with other extinction events further strengthened the impact theory. Tektites, small, glassy objects formed from molten rock ejected during an impact, provided further evidence. The distribution and age of tektites around the world helped scientists pinpoint the locations and times of past impacts. In 1991, scientists made a groundbreaking discovery that, honestly, revolutionized our understanding of the dinosaur extinction. They identified a massive impact crater buried deep beneath the Yucatan Peninsula in Mexico. This crater, known as Chicxulub, measured over 180 kilometers in diameter, a scar so large that it could only have been created by an object of immense size and power. The age of the Chicxulub crater, dating precisely back to the time of the dinosaur extinction, left little doubt about its significance. It was the smoking gun, the definitive proof that a massive impact event had coincided with the disappearance of the dinosaurs. The discovery of the Chicxulub crater sent shockwaves through the scientific community. It provided undeniable evidence that Earth's history has been punctuated by catastrophic impact events, capable of reshaping the planet and, well, altering the course of life. While the Nemesis and Planet X hypotheses initially provided compelling explanations for periodic mass extinctions, further research and observations really cast doubt on their validity. Astronomers, using increasingly sophisticated telescopes and extensive sky surveys, found no evidence of a companion star or a large planet lurking in the outer solar system. Moreover, the periodicity of mass extinctions, which was once thought to be remarkably consistent, came into question. More precise dating of fossil records revealed that the extinction events, while clustered, didn't actually occur at perfectly regular intervals. Furthermore, scientists began to unravel other potential explanations for periodic extinctions, such as the movement of our solar system through the Milky Way galaxy. As our solar system orbits the galactic center, it bobs up and down through the galactic plane. This movement could expose Earth to higher levels of cosmic rays and interstellar dust, potentially triggering environmental changes and possibly extinctions. With the Nemesis and Planet X hypotheses losing favor, scientists turned their attention to alternative explanations for periodic mass extinctions. One promising avenue of research focuses on Earth-based phenomena like massive volcanic eruptions and rapid climate change. Large igneous provinces, LEPs for short, are vast regions of volcanic activity that have been linked to several mass extinction events. These eruptions can release enormous amounts of greenhouse gases and toxic chemicals into the atmosphere, triggering runaway climate change, acid rain, and ocean acidification, which can devastate life on a global scale. Furthermore, Earth's climate is a complex and dynamic system, influenced by a myriad of factors, including continental drift, ocean currents, and variations in solar radiation. These factors can interact in complex ways, leading to periods of rapid climate change, which can put a lot of stress on ecosystems and, lead to extinctions. The story of Nemesis, Planet X, and the search for explanations for periodic mass extinctions highlights a fundamental aspect of science: its willingness to embrace new ideas, rigorously test them, and revise its understanding based on evidence. While these hypotheses ultimately fell out of favor, They spurred decades of research, leading to a deeper understanding of our planet's history, the dynamics of our solar system, and the potential threats from space. Science isn't about dogma or absolute truths. It's a process of continuous exploration, questioning, and refinement. As new technologies emerge and our understanding of the universe deepens, we can expect further revisions to our models and theories. The quest to unravel the mysteries of the cosmos is, honestly, an ongoing journey, driven by curiosity, observation, and the relentless pursuit of knowledge.